let's play around with the idea of solving systems of equations, and that is solving a cluster or a system of linear equations where there are more than one unknowns. And for now, the number of equations that you have must match the number of unknowns whose values you're looking for. So here we have two equations and two unknowns, so that's a perfect fit. Geometrically, what we're looking at here is whether or not there is a point of intersection between those two lines, because the solution to this pair of equations will be the x and y values both, which represents a point that both of the equations share. In other words, a point that's on both the first line and the second line. So where do they intersect? Now that's the geometric interpretation, but to find the solution, we don't have to actually start drawing pictures. What we're going to use is something called elimination. There are lots of different ways to work through solutions to equations. Elimination is a very systematic way, so that's the one we're going to tackle. So imagine that what we're going to do is take these two equations and add them vertically. What we would like to do is set it up so that when we add these vertically, one of the terms containing one of the other variables vanishes. So right now, if we just add them up as they stand, we would get a 4x, a 2y, and a negative 16. Well, nothing vanished. But imagine that if we took this second equation, again, which we are in charge of, and we can do anything we want to it, as long as we do it carefully, and something we do to it legally will not affect the solutions to it, we could multiply this equation on both sides by a cleverly selected number that then, upon addition with the row above it, would actually produce an elimination. And that number is positive 2. So what we're going to do is rewrite this system of equations, having multiplied the second equation by 2. We are allowed to do that. We are in charge. We have not affected the solutions. The solution to this pair is also the solution to this pair. And now, if we add these up, the solution we're looking for will still be hiding in the sum of the two equations. And when we add these two equations up, what we get is 7x plus 0y equals negative 21, or 7x equals negative 21, or x equals negative 3. So we have now discovered the magic value of x that is in the solution to this pair of equations, and now we can go back to either of the equations that we want and just use the value of x equals negative 3 to dig out the corresponding y value. So why don't we go to, say, the first equation and say, hey, equation, when the x value is negative 3, what y value do you have? And we ask the question this way by plugging in negative 3 for x. Then we get 4y equals negative 8, because we will add 3 to both sides, and so y equals negative 2. And so the solution to this pair of equations is a point that has the x and y values, negative 3, negative 2. And if we were to draw both of these lines on a set of axes, they would intersect at this point.